Okay, and on the last one, on number 6, we have, I'm going to put a little mark here because I might lose where I started. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's a dodecagon. If we draw all of our triangles, remember that should be 12 minus 3 diagonals from one point. So we would have 1, 2, 3, 4, 5, 6, 7, 8, 9. 12 minus 3 is 9 diagonals. The number of triangles created should be the number of sides minus 2, so we should have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. All right, so on number 7, we're going to write a formula for the sum of the interior angles of a polygon with n sides. So let me get out of this. Let's look at this animation. So let's start off with a triangle, 3 sides. We know its angles already add up to be 180. If we wanted to find the number of, or the angle of measure of just one of those angles, we would have to divide that 180 by 3. So each one of them is 60 degrees. So notice as I increase to a quadrilateral, the sum of the angles went up as well. So remember, we formed 2 triangles by 1 diagonal, and 2 times 180 is 360. So all 4 angles add up to be 360 since there's 2 triangles at 180 degrees each. If we wanted to find out what each of the 4 angles had to be, we would take that sum and divide by how many angles there are, which is the same as the number of sides. So 360 divided by 4 tells me each interior angle is 90 degrees. So let's go up to a 16gon. If we wanted to know what the sum of the angles is, then we really need a formula here because that's going to get a little cumbersome. But remember that the number of triangles we could form is simply the number of sides minus 2, n minus 2. And so 16 minus 2 is 14. 14 triangles, and then we just multiply that by 180 since that's the sum of the angles in any triangle. So that's where that 2,520 came from. It's the n minus 2, number of sides minus 2, that tells you how many triangles, times 180. Then if we want to find out what each interior angle is, we simply take that sum and divide by the number of sides. So 2,520 divided by 16 is this interior angle for each one of those. Okay, so let's look at your notes. Number 7, it says write a formula for the sum of the interior angles of a polygon with n sides. So this is for the sum. This is all of the interior angles added together. So we figure out how many triangles there are first by taking the number of sides and subtracting 2. And then we multiply by 180. So this is the formula that you're going to use to find the sum of the interior angles of any polygon. It doesn't even have to be a regular one. It can be any of them. So on number 8, we're going to be just for regular polygons finding the sum of the interior angle measure using this formula. And then we're going to find the measure of each interior angle, so each one. So remember, we're going to take that sum, which is n minus 2 times 180, and then divide it by the number of sides. That's how we find the measure of each angle in a regular polygon. We couldn't do this if it wasn't regular, because they could all be different amounts. So number of sides is 3. That's a triangle. This one we should have memorized by heart, right? That's 180 degrees. We put it in the formula. 3 minus 2 is 1, times 180 is 180. The measure of each interior angle would be that sum divided by the number of sides. So 180 divided by 3 tells us each one is 60 degrees. So these first 2 we should have pretty much memorized. For quadrilaterals, a regular quadrilateral would be a square. The sum of the angles, 4 minus 2 is 2, times 180 is 360 degrees, and then we take that sum and divide by the number of sides. 360 divided by 4 is 90 degrees. Each angle in a square would be 90 degrees. So here's where we probably don't have them memorized. We're going to have to actually use the formula. So for a hexagon, 6-sided figure, we're going to put in 6 for the number of sides. 6 minus 2 is 4. So we're going to multiply 4 times 180. So we should get the sum to be 720 degrees. Then we're going to divide that sum by the number of sides to get each angle has to be 120 degrees. So let's move to an octagon. With an octagon, 8 sides, 8 minus 2 is 6. 6 times 180 gives us an interior angle sum of 1080 degrees. Then we're going to divide that by the number of sides, and that tells me each angle is 135 degrees. A decagon, put in 10. 10 minus 2 is 8. 8 times 180 is 1,440. And then to find each angle, we would simply take that sum and divide by 10. So each angle would be 144 degrees. Now that we have done pretty much all of these, I want to show you a way that you could use your calculator and make this a little bit even faster. You could go to your y equals, clear out anything that you have there, type in your formula. So inside parentheses, I'm going to use x instead of n, but it's the same thing. X minus 2 times 180. And then I can look at my table, and it shows me for a 3-sided figure, that's 180. 4-sided, it's 360. 6-sided, 720. 8-sided, 1080. Do you see how much faster that is? There's 10-sided at 1440. So to get to 20, I'll show you another thing that you can do with your calculator is go to your table settings, which is above window. So go to second window, and you get to tell where your table starts. So instead of scrolling all the way to 20, I'm just going to tell it to start at 20. And then look at my table, and it tells me if it has 20 sides, the interior angle sum, I don't know if you can see that, is 3,240 degrees. And then 100, I would go to my second window, table set, say start at 100. Go to my table, and it tells me a 100-sided figure. The interior angle sum would be 17,640 degrees. And then for 1,000, go to my second window, tell it to start at 1,000. Go to my table, 179,640 degrees. Now if I want to know what each angle measure is, I'm going to go back to my y equals, and then I'm going to divide this by x, which is the number of sides. So now when I look at the table, it's telling me what each angle measure is. So let's go back to 20-sided. So I'm going to tell my table to start at 20. And so looking at my table, each angle would be 162 degrees. So again, I could do that by doing this divided by that, but I'm just having my calculator do it for me a little bit faster. So go to my table setting and start at 100. Go to my table. That tells me each angle is going to be 176.4 degrees, which is easy. Dividing by 100, we've just moved that decimal 2 places to the left. And then I can go to table setting and start at 1,000. Go to my table. That's 179.64 degrees. Now, I want you to see, when you get to calculus, you'll be talking about what are called limits, and you'll talk a lot about as we approach infinity, what's happening with different values. So I want you to see that this measure of each interior angle is getting larger and larger and larger. It's approaching 180 degrees, which is a straight angle, but it will never ever get to 180 degrees because then, you know, it wouldn't be an angle formed by 2 vertices in a polygon. It would have all 3 vertices in a row, so that wouldn't make sense. So we're going to get really, really close to 180 the bigger we make this number, but we would never actually reach 180 degrees. So we already did number 9 in our notes. It says write a formula for the measure of each interior angle of a regular polygon. Remember, we can only do that for regular because with irregular, all the angles would be potentially a different measure. So we already said our sum is n minus 2 times 180, and we have to take that sum and divide by the number of sides to get each angle measure. So that is the formula that you should have on number 9. All right, so we have done all of these things. Let's look at question 10 in your notes. It says, now that we know about the interior angles of regular polygons, think about the hexagonal floor tile again. Why can regular hexagons be used to tile a floor? What other regular polygons could be used alone to tile a floor, and why? So I want you to see where the hexagons meet together at a single vertex. So I'm going to use red there so it kind of shows up a lot. These angles, this one, 1, this 2, it's kind of hard to write with this, and this one 3, these angles right here come together at that single vertex. And so you can kind of see I can kind of make a circle through here. So these 3 angles have to add up to be what? How many angles or how many degrees are in a circle? 360 degrees. Well, you can see from our notes that we said that in a regular hexagon, each of the angles is going to be 120 degrees. And we have how many of them? 3 of them. What does 3 times 120 equal? 360, right? They have to add up to be 360 to work for a tile because of the 360 degrees in a circle. So what other regular polygon do we have that we can have a certain number of those angles and it come to 360? So could we do a regular triangle? Yeah, how many of those would we need? We would need 6 of them. 6 times 60 is 360. So yeah, we could use a triangle. What about a square? Yep, 4 times 90 is 360. And hexagons, we already said, yes, 3 times 120 is 360. What about an octagon? Well, let's take 360 and divide it by 135. We get a decimal amount, right? So octagons won't work. What about decagons? We'll take that 360 and divide by 144, and we get a decimal again. Okay, so that's how we can tell if they can work in a tile or not, is if the interior angle is a factor of 360. That's the key. So it says, why can regular hexagons be used to tile a floor? Because they can come together to make 360 degrees. What other regular polygons can be used? We can use a regular quadrilateral, which is called a square, and we can use regular hexagons. And again, for the same reason, they come together to make 360 degrees. All right, so how are interior angles related to exterior angles? Let's go here and let me draw an exterior angle by extending that side. So we're talking about how does this angle relate to this angle, and we've talked about that before. They are a linear pair. They make a line together. So that means that they are supplementary to each other. All right, so your homework is assignment 17.1. Good luck.